Greetings friends, I am Sanjay Mittal from Department of Aerospace Engineering, IIT Kanpur, and I would like to introduce this course to you, Computational Fluid Dynamics using the finite element method. So, computational fluid dynamics is now a very mature subject. It is being used widely for a variety of things in science and engineering. For example, if you want to design an airplane or you want to design a hypersonic vehicle, you use the methods of computational fluid dynamics. It is very common in sports. For example, if there are a couple of cyclists and the question is who spends less energy, the person who leads the trail or the person who is downstream of the cyclist. So, who spends less energy? If you are doing swimming, then what should be the hand position, what should be the strokes, so that you spend as little energy and possibly can win an Olympic record. If you want to design badminton shuttlecocks, for example, so you have these synthetic shuttlecocks made out of nylon and you want to do as good as the feather shuttlecocks, you can again use the fluid structure interaction of computational fluid dynamics. Motor sports, soccer balls, the list is endless. So, this finds its applications in various science branches of science and engineering. So, you want to know what is this computational fluid dynamics? Well, we are going to model the flow through a set of equations. So, we use the balance laws such as the mass balance, force balance, energy balance, laws of thermodynamics and so on. Also some laws of constitutive modeling of the matter. For example, it could be a fluid, you could assume it is a Newtonian fluid or a more complex fluid, and you get some governing equations. Unfortunately, these equations are very complex. They are coupled because there are many unknowns, they are highly nonlinear, and these are partial differential equations. So, most of the times it is not possible to get a closed form solution and therefore, we resort to numerical techniques. So, we will take these equations and try to figure out a way to solve them on the computer. There are many numerical methods available. There is a list given here. So, you could have the finite difference method, you could talk about the finite volume method, the spectral method. Of course, in this course we will talk about the finite element method. There are many other methods as well, boundary element, and the list goes on and on. So, what is the finite element method for fluid dynamics? Well, the traditional method was derived for solid mechanics by a person called Bubnov and another scientist called Galerkin, and it works extremely well for solids. Unfortunately, it does not work too well for fluids, so there are some tweaks that are needed. So, actually the aim of this course is to treat you, give you an introduction to both these applications. You want to learn about what is the traditional finite element method, which is the Galerkin method, and also what are the tweaks that you need to make to work it for fluid mechanics. So, I want to show you a little bit about what the course plan is. We will follow very logically the development of the finite element method and then apply it to problems in fluid mechanics. So, some of the topics that we will cover are, we will start with a very simple introduction to some of the mathematical preliminaries that we will need. For example, the basic vector spaces, what is a basis set, the idea of completeness, functions being continuous and differentiable and how you quantify that. Then we will introduce the method of weighted residual. This is the general method which can be used to solve any partial differential equation, and basically we will learn about what is error and how to control it. So, the way we control the error, the philosophy of it gives rise to various methodologies, and one of them being element method, another being finite volume, yet another being finite difference, and we are going to be able to see what is the difference between these methods. Now, we will be ready to apply the traditional finite element method to a problem. So, we will start with a very simple toy problem, a one dimensional steady state linear problem, just 1D heat conduction. We will look at the strong form of the problem, the original differential equation, then we will cast it in a weak form which is amenable to finite element method. Then we will make some approximations, because when you are doing numerics, obviously you are happy with the approximate solution, not the you can never hope to get the exact solution except in exceptional cases. So, we learn about what are the finite dimensional spaces, what are the interpolation functions or the basis functions that we will use, how we get the matrix form, and we will give some examples. Next, we will learn about how to deal with a linear finite element space and how to implement this method on a computer. So, there are some techniques that can be used to simplify the implementation. So, once we have learned the one dimensional method, then we are going to go ahead and generalize it in 2 and 3 dimensions, and also then we will talk about what happens if at a given point there is more than one unknown. So, for example, if you look at fluid mechanics, then if you are solving incompressible equations in 3 dimensions, then at each point you could have 3 velocity components and a pressure. So, you would have 4 unknowns. So, how do you deal with vector unknowns? Then we will go ahead and talk about how do you generalize these methods for higher order accuracy. So, we will talk about basis functions and how to generalize them to higher order. Then we will talk about how to take derivatives of these basis functions and implement them on a computer. Of course, the method involves integration, so we will learn about numerical integration next, and then comes how to solve time dependent problems, because most engineering problems are time dependent. So, we will look at the numerical framework, we will talk about the stability analysis of these methods, the time integration schemes, their error analysis, and this part actually is applicable to all methods, not just the finite element method. You could possibly use them in finite differences and spectral methods and so on. Having done that, now we will move our attention to nonlinear problems. So, how do you solve a nonlinear problem? So, usually the method is you linearize it locally, and for that we will use the standard Newton-Raphson method. It is a second order method, and then how do we implement it in the finite element method? I will talk a little bit about that. Once we are ready with this, we are actually ready to go into fluid mechanics. So, as I said earlier, that the traditional finite element method gives some problems with the fluid mechanics problems. So, how do you get around them? So, we will talk about this so called the SUPG method, the streamlined upwind Petrov-Galerkin method. It has some parallels with finite difference methods which are upwinded. So, we will talk about that, and then we will use these methods to talk about solving incompressible and compressible flows, and finally, we will wrap up with some case studies. I will give you some ideas of high performance computing, some application problems, and that is pretty much the end of the course. So, see you in the course. Thank you very much.